Hey there, my fellow intellectuals. Welcome back to part 2 of this problem, where we're now going to determine the conditions for a circular orbit for the little m, the little mass, and then we're going to determine the radius at which this occurs. And there's this annoying little g above that came down from copy and pasting, but now that's gone. So let's go ahead and begin with figuring out what's the condition for circular rotation for little m. So remember, little m is way back up here, and it's attached to the string. And one condition for circular motion that we definitely need is that to have a perfectly stable circular orbit, well, we need to have a definite radius for that orbit. What does that mean for the change of that radius? Well, that means as time goes on, the radius of that orbit needs to stay constant. That radius needs to stay the same. So the condition that you need for a circular orbit for little m condition is we need the velocity of the position, right, of the position variable, that radius r. We need r dot to equal 0, and we also can't allow that thing to accelerate. So that means that r double dot must also equal to 0. So if we look at our equations of motion, the first equation of motion in particular, we'll notice that if we let r dot here be 0, we get the following equation. mr dot squared minus mg is equal to 0. So that is the condition for circular motion for little m. I'm actually going to rewrite this equation in a more maybe intuitive way. We're going to substitute the angular velocity, right? We're going to rewrite it in terms of, we're going to rewrite theta dot in terms of the angular momentum, and we're going to stick it into that equation of motion. And from that, we're going to look at the radius at which a perfectly circular orbit will occur. So let's go ahead and do that. We're just going to say L divided by mr squared is equal to theta dot, okay? And if we plug this expression into here, we'll have little mr. Now we have to square everything in this equation. We'll have angular momentum squared, m squared, little r to the 4th, subtract big mg is equal to 0. And we're going to look for the equation, we're going to solve for r in terms of everything else to determine what that radius needs to be. So, okay, let's go ahead and try and solve for r here. It's just a tedious algebra problem at this point. So we're going to cancel 1m from both top and bottom here. We're going to cancel an r from top and bottom here. And so the equation now reads L squared over mr cubed minus big mg to 0. And now we just have to be careful with our algebra, so I'll just add the big mg to the other side is equal to big mg. Now we have to flip this fraction, so we'll have mr cubed over angular momentum squared, that's equal to 1 divided by big mg, and then we'll multiply L squared and divide by m on the left side, so we'll have r cubed is equal to L squared over little m big mg. And finally, the radius is now determined by just taking the cube root of each side. So we'll have angular momentum squared, little m big mg, all of this to the 1/3. And so this is the radius at which perfectly circular rotation occurs for the little mass. So I hope you found this video helpful. I hope it was a good review or test of your Lagrangian mechanics, and I will see you next time. Thank you for watching.